What's up, everyone? Welcome back to Speed, Math, and CS. So today we are going to be continuing our study of AP Physics C, Electricity, and Magnetism. And today we are going to be studying Unit 3, which is going to be Gauss's law. So essentially, to start off today's lesson, we are going to be introducing a concept called electric flux, right? So for flux, we're going to be using a variable like so, right? That is going to be our flux variable, right? And this is going to be equal to the dot product of A, right? Which is an area vector. And multiply it by F, right? Which is going to be the constant vector field. Remember, in this case, right, we're not yet looking at an electric field quite yet. We're just simply introducing the concept of electric flux. So now, if we remember from Unit 1, right, in order to simplify this dot product formula, this simplifies to AF, right, where A and F, the magnitudes of A and F respectively, times cosine theta, right, which is basically the angle between the two. But if you look at this real quick, right, both of these are vectors, right? But you're gonna be like, hey, what? How is there a vector for area? Isn't area just a constant scalar we use to measure like the area of like a surface or something, or just like surface area? But in fact, the area vector is essentially that same thing, right? Where the magnitude, like, let's say we have a square, like so, right? A square with like some thing in between, right? To calculate the area of the square, right, we go width times height. That's the magnitude of the vector, right? But the direction of the vector is actually coming right out from this square. So it'll be coming out of the screen like so. So this is what our area vector will look like. And then of course a vector field can be anywhere. Like for example, there could be a vector field going like this, right? It could be going like this. Yeah, something like so, right? So there could be any vector like this. But that's essentially, the area vector is out of the surface where you're measuring the area. That is the area vector, right? So, yeah. So it's defined as a vector with magnitude equal to the surface's area and direction perpendicular to the area. And later, right, you might notice that this can go in two directions, right? So a surface has two sides. So you could be like, hey, why can't the vector go out from here? Later down the line, we will be introducing a thing called the right-hand rule, which we'll determine essentially using your thumb which direction, either backwards or basically into the screen or outwards, will this area vector be pointing. So what exactly is flux in the first place? So if the vector field is a constant velocity field of a liquid and the surface is a square wire frame, the flux has a simple physical interpretation, which is the volume rate of flow liquid through the wire frame. So essentially, think about it like this. Let's say we had a square, we had a surface like this. Let's say we had a surface like this. And essentially the amount of, now let's say we represent the vector field in terms of bullets, right? So the amount of bullets passing, let's say the bullet passes through that, then we shoot another bullet, passes this. So the amount of bullets piercing through that surface is essentially your electric flux. It is essentially your flux, right? So now this should make sense, right? Because if the maximum electric flux will essentially be if this is parallel to, like, let's draw more lines, right? If this is parallel to the electric field, right, then it'll be essentially getting pierced through the most amount of bullets. And if it's perpendicular to the electric field. But now let's say it's parallel to the electric field, right? It's perfectly parallel, like so. Right? Where the bullets are just shooting like this. So in this case, it's completely it's just completely parallel, and there's no bullets getting pierced through this surface. So this should make sense, because in our formula up here for flux, right, it's the area vector it's the magnitude of the area multiplied by the magnitude of the vector field. Sorry, I don't know why. But times cosine theta, right? And essentially, if you think about it, right, in terms, this cosine theta has a value between -1 and 1. So the thing is, the cosine theta actually it just limits this value of a times f. Sorry, but in this case, right, where we have parallel area, our area vector is shooting out in the same direction, so it's parallel, right? So the area vector, the cosine theta, like the angle between the two, is 0, and cosine of 0 is 1. So in this case, right, the flux is simply the amount of area multiplied by the amount f, or the vector field, which is essentially the number of these sort of bullets that are going through. And this should make sense, right? Because the larger the area of the surface, the more bullets can shoot through it, and the more amount of bullets, the more bullets will actually pierce through. So this should make sense. Now looking at this parallel field, right? This is like if you took glass and stuck it horizontally and then tried to shoot bullets at the glass. You're not going to hit it, because you're essentially shooting at like an infinitesimally small area. So in this case, where the area is like this, none of the bullets will pierce through. And this makes sense, because if you think about it, the area vector this time is coming right out of the screen like so. And it is at a right angle with the electric field lines, or the bullets. So cosine of 90 is just 0. So in this case, there is 0 electric flux. Another important thing, right, is another important thing to understand is the fact that, well, at least for this, for understanding flux better, let's take a look at like something like a sphere, right? So I will try my best to. So we'll have a sphere. So let's say we have a cross section of a sphere, right? And then we have some electric, like, point charge inside of here that sends these electric force, like electric field lines, out. So in this case, these will be like the bullets that we have. And assume I just took a cross section. So assume that this is a sphere and it's going out of the sphere. So in this case, bullets that go out of the sphere are considered positive electric flux, right? If we have a bullet like here, starts here, and it pierces through like so, goes this way, that's positive flux. If, for example, we have another, let's say, for example, we had another point charge here, right? And now it's sending bullets inside the sphere. Sending bullets inside the sphere is negative electric flux. So in this case, right, what we can do to represent electric flux, once again, right, we'll use our flux variable. But essentially, the flux variable is like so. So the electric flux, which we denote like so, flux electric, is equal to the closed loop integral, right? Essentially here we have a Gaussian surface, which we'll cover more later, but essentially here we have a Gaussian surface, and this circle in the integral sign essentially means around that enclosed surface of the electric field, right? Multiplied by dA, or essentially dot product with dA, right? So this is sticking to our formula up here, but this time we are integrating with respect to A, because in typical problems involving Gauss's law, our A will not be constant, right? So, or our A, there'll be different area vectors. Like, for example, in the sphere over here, right? The area vectors are shooting in multiple different places, right? So in this case, we don't have a constant area vector. Our area will always be constant, but the direction is really why we have to go integrated. So get this idea in your head, because this will appear so much more throughout AP Physics C, electricity, magnetism. But essentially, whenever we can't really measure something, whenever we can't assume something to be constant, or in essence, when it can keep changing, right? Remember, calculus is the concept of change. So whenever we say something is changing, we instantly think of calculus. And what do we do when we think of calculus? We think of integration. So I know that that's a weird analogy, but essentially what we will be doing is we just took that formula from earlier and then just integrated it with respect to area. So it'll appear like so, with the differential multiplied by the electric field. So this is our electric flux. Okay, I know that was a lot of talking about electric flux, but let's actually get into the juicy stuff for today. And by juicy, I mean we're talking Gauss's law. So Gauss's law is actually a bit of a corollary of Coulomb's law, and the two are essentially equivalent. But the thing is, Gauss's law can be very efficient and can be applied in many different scenarios. If you're taking AP Computer Science A, for example, you'll know this is the difference between something like iteration or recursion, right? In certain cases, iteration will be better, but in other cases, recursion might be better. But essentially, they're going to be accomplishing similar tasks. So in this case, right, now that we're familiar with calculating the electric field of a charge distribution via Coulomb's law, right? This is what we've been doing for the past 2 units. So by now you should be familiar with this. However, calculating the electric field due to complicated continuous charge distributions can be difficult using Coulomb's law, right? And essentially, Gauss's law is another way to calculate electric field. Like we covered before, Coulomb's law is the equivalent to Gauss's law, and which approach depends on the problem. And in some cases, both can be used. So let's actually think about what Gauss's law would be, right? So, or let's actually get a little more context on the electric flux before we move into Gauss's law. So, essentially, if we go back to this example here, right? And remember that point charges always produced infinite electric field lines. So essentially with Gauss's law, right, we're gonna be taking this formula, right? So we're gonna be taking our surface closed integral, or our formula for electric flux, times the small dA vector, and then we're going to be equating it to something, right? Something, which will allow us to somehow calculate the electric fields easier. But essentially, if we want to equate it to something, let's just think about the idea behind what we could do. And this is solely so you remember actual Gauss's law, which I'm sure you'll remember after a lot of practice, like what can be found on homework speed.mathcs.glitch.me. So be sure to check that out if you haven't already. But essentially, if you think about it, right, a point charge inside of the sphere will be sending a bunch of bullets out of the sphere. So it'll have a positive flux on the on the sphere itself. But if you think about it, bullets outside of the sphere, right? These will essentially these will be sending bullets into the sphere. But those same bullets, because they're infinite, let's actually, just to make this more clear, right? Like so, right? We'll have a bullet like so that pierces through right here and then comes out right here. So it pierces in here, which is negative flux, right? Negative flux. And then it pierces out, which is positive flux. So in fact, these two cancel out, which allows us to determine that Gauss's law will only care about the charges that are enclosed inside, because those are the only ones that will contribute to the electric flux. Outside charges do not change the electric flux. So if we want to have something equivalent to the electric flux, like so, we are only going to be considered charge that is enclosed inside. So Q enclosed. So the electric flux will be equal to the charge enclosed divided by another variable we introduced, right? Which is the electric permeability of space. And remember, we introduced this variable we introduced a little corollary of this variable as K, which will equal to 1 over 4 pi E naught, right? And we said that this was 9 times 10 to the 12. But essentially, this K for this will be useless. We are going to be actually digging into this electric permeability of space with Gauss's law. So this electric constant is equal to approximately 8.85 times 10 to the negative 12. So to the negative 12, right? In coulombs squared divided by newtons meters squared. Sorry. Yeah. So it'll be in this. Coulomb squared divided by newtons times meters squared. This is the units of the electric permeability of space. Actually, let's just make this less confusing, right? So E naught, this is what E naught is equal to. E naught is equal to 8.85 times 10 to the negative 12 Coulomb squared over newtons times meters squared. These are the units. So if we look back here, this should line up, right? Because we know that electric field is the measure of newtons divided by coulombs, right? Yeah, newtons divided by coulombs. And then we know that area, once we integrate it, will be in the form of meters squared. Once we integrate it. The dA, right? Remember, dA, before we integrate it, will be in the form of meters. But the area vector after we integrate it will be in meters squared, right? Which is equal to, charge enclosed is C divided by E naught, right? Which will be N, which will be Coulomb squared, right? Divided by Newton times meters squared. And as you can see, this lines up. So we know our formula for Gauss's law is correct. So in this case, right, if we were just to consider the charge enclosed and say that it was equal to the flux, we would see that our units are wrong. Which is another reason, unit analysis, which we learned in the very first unit, this is another reason why it is so important. So now let's consider Gauss's law for what it actually is, right? So remember that electric field lines begin or end only on positive and or negative point charges, respectively. And the number of field lines that begin or end on a point charge is proportional to the charge's magnitude, right? So think, essentially going back to our bullets example, the bigger this charge is, like if this, let's say this charge was 12 coulombs, it's gonna have more bullets to send out, which will which, as we know here, right? Because charge will become larger, right? It'll be like 12 coulombs. You'll see that this numerator will become larger, more bullets piercing out. So this actually makes sense with our Gauss's law interpretation, right? So within this framework, it's easy to understand why charges outside of a surface contribute no net flux. So it's the same example here, right? Where piercing into this object will cause negative flux, but then piercing out of this object will cause an equivalent positive flux in the opposite direction, and the two will cancel out. So now let's actually use this formula in order to determine electric field. So I've been talking so much about electric flux, but how the heck are we even going to use this formula to find electric field, right? Because we've been just talking about electric flux, but we've never even mentioned electric field. And remember, I said that this was going to be a corollary to Coulomb's law. We're going to use this to calculate electric field. So let's actually get into how we are going to be able to do that, right? So in a typical Gauss's law problem, right, something typical you'll see on an FRQ or an MCQ, you are going to be given a charge distribution, right? So, and this is going to be a continuous charge distribution like we learned in Unit 2. So, this can be like planar, something like so, right? So something like so. Something like so, right? Something like so. And it's gonna essentially have a linear, it's gonna have, for example, charge density, like so. If this was a line, right, we would have a linear charge density. So you're gonna be given the two things, right? Either an infinite, planar surface, infinite line, or something like this, and the charge density, right? So then, in order to, and your goal will be to calculate the electric field created by this charge using Gauss's law. And remember that while using Gauss's law, it's always valid and is only used as a calculational tool for charge distributions with the following types of symmetry, which essentially means this is the only things you'll be seeing on the AP Physics C Electricity and Magnetism exam is things with the following types of symmetry: planar symmetry, cylindrical symmetry, or spherical symmetry. Essentially, you will be able to, we're going to be getting into Gaussian surfaces later, but you are going to be essentially you're only going to have to use one of the three Gaussian surfaces. So either you will use a Gaussian box, like so, which is just a rectangular prism, right? And I know that is a very horrible drawing, right? So like so, a cylinder, right? Or a sphere, right? Assume this is a sphere, not a circle. And our box here is going to be used to evaluate 2D, right? 2D things, which will have a planar charge density, right? So something like so. I don't know why I keep putting a slash there. So it'll be 2D and use this charge density. A cylindrical will be used to evaluate single dimension objects, like a line passing through the cylinder, like so, right? We'll use a cylinder for that type of symmetry with single dimension and a linear charge density, and a sphere will be used to encapsulate 3D objects, like a box or something, inside of the sphere. So 3D objects and we'll have volumetric charge density. And today we will be looking at an example for all three of these, right? Where we'll be looking at an example for all three of these. We're gonna do a problem where we first use the box, a second one where we use our cylinder, and a third one where we use our sphere. So essentially, to find the electric field at a point in space, you must create a Gaussian surface, right? One of these three Gaussian surfaces, because these are the only ones we're going to have to use on the actual AP exam, right? And essentially, a useful Gaussian surface has symmetry that mirrors the symmetry of the charge distribution. So if we think about it here, we have an example like so, where we had a line passing through the cylinder, and so like this. In this 3D example, we're gonna essentially, so we're in a sphere example, we essentially boxes or 3D objects that will go out, and then for the 2D object, right? I don't think I quite mentioned this, but essentially it'll be evaluating a plate like so. So if you notice for these, right? The reason we call them symmetric, right? Let's say it's something like this, right? Is that our cosine theta, remember, that's gonna be our electric flux. So that is always gonna either be like parallel or perpendicular. That is our goal. So if we think about it, like we had a point charge here. This property of geometry states that anything coming out is always perpendicular to the sphere. And then essentially, this can be used for 3D and 0D. So like point charges will be 0D. So like for most of the time, we're just gonna use our corollary Coulomb's law for electric field, but this should just give you an idea of how we use Gauss's law to solve for 0D. So this can be used for 3D and also point charges, right? We can use a sphere to evaluate point charges. So essentially, if you think about this, like a point charge, for example, it's only ever going to have stuff that's perpendicular, meaning it's very simple. It's just the area multiplied by the magnitude of this field line. Super easy. If we think about the cylinder, right, because it's encapsulating this line, like so, we're only ever going to have stuff that's parallel, like so, where the area vector is perpendicular to the electric field lines, or essentially there's going to be a line inside. And because we're using a cylinder, once again, it's always going to be perpendicular or tangent to the outside surface. And same thing with this box, which should be pretty obvious why it's symmetric, right? All the sides are always parallel, and like the tops and bottoms will always be perpendicular, like so. So that is what we call highly symmetric in AP Physics, at least regarding AP Physics. See electricity and magnetism. So now, so with the choices of So with these choices of surfaces, there are regions of constant electric flux, right? And possibly regions of zero flux because the component of the electric field parallel to dA is 0, like we mentioned here, because it's parallel, right? And this will make it easier to calculate the electric flux integral as we will now do a practice problem where we do so. So let's start off with planar symmetry. So for problem number 1, right? For problem number 1, we are tasked with evaluating the electric field produced by an infinitely large sheet of charge with the uniform charge density positive rho coulombs by meters squared. So essentially, we have a plane like so, right? And we are with positive rho charge density across it, like positive rho. So I know that's actually horrible rho. It looks something like that. But this looks more like a 6 than an actual row. But yeah, you know what I mean. But let's say we have a planar charge distribution like this. We are trying to evaluate the electric field, like these electric field lines that are coming in and out of the sphere. So, like so. So in order to do this, right, because it has planar symmetry, right, like we set up here, and it's a 2D surface, we're going to be using a Gaussian box in order to solve this. So let's actually let's get rid of this weird like row symbol here. And let's stick in our Gaussian box, right? And with this Gaussian box, we want to ensure as much symmetry as possible. So we'll stick the Gaussian box in here such that it's exactly halfway. So if we're considering a cross section of like this side, for example, let's say we're considering a cross section of this side, right? It'll be like this, and then we're looking the plane is essentially right here, right? And this is the box, which is exactly halfway through. This is how the sides are gonna look. And now with this, and like for the top, obviously it's gonna be just like how we place it. So these are what the sides are gonna look like. It's gonna be exactly halfway through to ensure the most symmetry as possible. So now let's try to evaluate the electric flux, right? Because remember Gauss's law, right? The Q enclosed, right? Like remember we're going, Gauss's law here, right? To evaluate electric field, we have to get this Q enclosed on its own side. So typically in Gauss's law problems, you will calculate the electric flux, right? And the electric field is given by Q enclosed. So you can go from electric flux to electric field. Like that combination is what is the ratio of the permeability of space. It is the electric flux divided by the it's the electric field divided by the electric flux. But typically, we're not tasked with finding the electric flux. It's just helpful we understand this such that we have an easier way to convert it into electric field. So we are trying to find Q enclosed. So in order to do that, we need to find E naught, which we've already found here. And we need to find the electric flux of the particular shape. So in order to do this, the electric flux of the Gaussian box is essentially the number of bullets, right, that are piercing through it. So in order to do this, right, because different sides will have different numbers of bullets piercing through them, we'll split the flux up, right? So electric flux will be equal to the enclosed area will essentially be the enclosed area of the box of E times the dA vector, right? And essentially we can split this up into we can split up into all of the sides, right? All of the sides. And if you aren't sure that the sides are all equal, in this case you can always split it up into like right side, left side, front, back. But in this case, we know the sides are equal because they all share this. Remember, it's an infinite charge distribution, so it extends in all infinite directions. So all the sides are going to look something like this. So we only need one integral for that. And now, so it's gonna, for this, we're gonna add the top, because the top actually and bottom have like bullets piercing through them, so we'll evaluate them separately, right? Top and bottom, right? But if we think about the sides, so the sides, right, we can think of this in two ways. Firstly, we'll use our bullet example, right? So if we have a plane here and we're considering the sides, we're shooting bullets like this. But if we think about it, it's like if we had a paper here and we tried to shoot bullets, like if we had a paper here and then we tried to shoot bullets through it. You're shooting it through this infinitesimally small like area. You're trying to shoot bullets like that, right? So we're not gonna actually get any bullets piercing through this side. And this actually goes for all the sides. We're gonna have 0 bullets piercing through them. And additionally, we can see this, right? Because the electric field comes out like that. From a surface, the electric field comes out like this and below like this, right? So essentially this area, right, will have an area vector like so. It'll come out like this. And the electric field line is like this. These two are at a right angle. They're at a right angle. So the cosine will just be 0. So these sides actually don't even matter in this case. So this entire expression right here becomes 0. So now let's go through evaluating the electric flux through the top, right? So through the top, right? We have something that'll look like this, right? Where we will have the thing like that, and then we will have something like that, right? So all the bullets are actually gonna pierce through. Every single bullet is piercing through. And remember, the area vector is directly parallel to this. So thus, the cosine theta will just be 1. So this is equal to E times A, right? And we'll see us like this right here. Top is equal to E times A. And same thing with the bottom, right? The bottom and top are symmetric. It's the same thing, E times A. So if we add up all of these expressions together, right, we will get that this is equal to 2EA, right? Which means that sorry. So actually, in this case, we're not using Q enclosed. I got it. But this is equal to 2 times the electric field of it multiplied by the area. So now, in this case, we've evaluated the first side of our Gauss's law equation, essentially, right? So essentially, our whole closed loop integral has come to 2AE. 2 times the area times the electric field will be equal to Q enclosed. Closed divided by E naught. So what exactly is Q enclosed? So Q enclosed, right? Remember from the problem, right? So Q enclosed is the amount of charge that's actually enclosed. And the only thing we're given in the problem is that we have a charge density rho, which will be equal to the charge divided by the area. And in order to get just the charge itself, we just want what's up here. We don't want area. So we will just multiply by area here. We can multiply by area. So Q enclosed is simply equal to the charge density multiplied by the area. So we will get something like so. 2AE will be equal to the charge density multiplied by the area over E naught. And essentially, when we divide such like this, we divide both sides by 2A, we get that electric field equals the charge density divided by 2 times E naught. And in fact, write this down because we have just proven a formula, right? The electric field of an infinite plane of charge with charge density rho is equal to rho divided by 2 times E naught. So there we go. So now let's try to do something similar. Let's do our second example problem. And we'll probably end off of this. So hopefully Gauss's law is starting to make a lot of sense for how we actually apply this. We are essentially taking our electric flux, right? Electric flux in this case doesn't matter. We're just using it to evaluate the electric field, right? The electric flux is some function of the electric field, and we're using this equation to isolate this E variable, which will give us the electric field. So you can see how Gauss's law can be used to determine this. So now let's actually go through a second problem involving Gauss's law. So in this case, we are going to be looking at a 1D example, right? So let's say we have a sphere like so. Or no, what am I doing? No sphere. Sorry. In this case, we're tasked with calculating the electric field produced by an infinitely long line. Right, infinitely long line. Like so, with charge density of lambda, right? So in order to do this, right, remember from up here, to evaluate a single dimension, we use a Gaussian cylinder. So let's draw on a Gaussian cylinder, like so. And we will keep it such that this line, I know it doesn't look like it, but assume that this line pierces through the center of this cylinder because we want as much symmetry as possible. So in this case, right, for the cylinder, right, we have a bunch of different faces, right? We will have the top face, the bottom face, and the entire other stuff, like this curved face over here. So in order to evaluate the electric flux, right, whenever doing a Gauss's law problem, first thing you do, evaluate the electric flux, left-hand side of the equation. So in order to evaluate the electric flux, right, the flux will be equal to remember the enclosed area by I don't know why I put cylinder out here, right, which will be equal to the enclosed area of E times dA, right? And like we said, right, we're going to isolate these into several integrals, right? We're going to have an integral for the top, we're going to have an integral for the bottom, and then we're going to have an integral for outside or the curved edges. Actually, we'll just say other here. Everywhere else. Because remember that cylinders have the property where any line intersecting them is perpendicular. So everywhere else. E times dA. Like before, what we'll notice is that in our problem with the tops and bottoms, this line, right, will be essentially sending bullets in all directions like so. It'll be sending bullet here, bullet here, bullet here, bullet here, like so. It'll essentially be sending bullets like that. And if you think about it, this top and bottom spheres are literally parallel to the bullets. So they're not going to get pierced by any of the bullets. And if you think about it, right, the area vector, like we defined earlier, right, the area vector like so is literally perpendicular to where the bullets are going at. They're literally, any given bullet, it's perpendicular to it. So the cosine theta, the cosine 90 is just 0. So these top and bottoms have failed. They have no bullets passing through them. Literally useless. So these are, well, actually, okay, I'm being harsh, but it's actually good that these cancel out, because now all we have to do is evaluate the flux everywhere else, right? 0, 0. So now, if you think about it, right? In this case, right, the electric flux coming out from this side, right, is simply so it's simply equal to because it'll always be perpendicular to the sphere, right? And remember, because we're using dA here, the everywhere else has a bunch of area vectors, right? Area vector here, but regardless of that, the bullets will always be parallel to them, right? Because remember, our sweet geometry function, right? If we have a thing like that, and a circle with a center like that, and it sends a bullet out, it is always going to be tangent to this section right here. So it's going to perfectly pierce it, and so cosine 0 is 1. So in this case, this just becomes E times A. So now if we go back to our Gauss's law, right? This time, remember for the last one we had 2 EA, this time we just have EA, right? Or, as a draw, yeah. EA, which will equal to Q enclosed over E naught, right? So, if we think about this, right, with E naught, sorry. Yeah, so E naught, right? So for the charge enclosed, right? The charge enclosed is simply going to be the charge divided by area, which is our linear charge density, right? So E times A will be equal to the linear charge density multiplied by the area, right? Or no, linear charge density multiplied by the length. Right? Will be multiplied by the length. So yeah, give me a second, I'm just checking real quick. Sorry. Give me a second. Yeah. So yeah. Sorry. So this will be equal to this divided by E naught, right? But if you notice here, look at this. We have so many pesky variables. A, L. This doesn't help us. Like, if we're trying to evaluate the electric field, there's no area, there's no length. Like, come on, it's an infinite length, and what even would be the area? We're trying to evaluate the electric field, not some like area of some surface, right? We have to cancel these variables out. They're just pesky. And literally, if you think about if you gave this equation to like one of your classmates and told them, hey, I think EA equals to linear charge density times length over E naught, use this equation to evaluate the electric field from an infinite line. They're going to be like, hey, are you crazy? The length of a line is literally infinite. And what even would be the area of a line? The area of a line doesn't even exist. That's not even a property of lines. So we have to cancel out all these variables. So in order to do so, like we last problem, the area canceled out. So we didn't have to do this. But for this problem, we are going to have to break up this area into the components of a cylinder. So remember, the area of a cylinder is 2 pi r, right, which is the base, multiplied by the height. In this case, will be L, right, multiplied by E. And remember, okay, so before you think of this as a dot product or anything, this is a scalar, remember? So scalar multiplied by vector is just, it doesn't matter, right? So remember, we learned scalar multiplication in the first unit. So times L E naught, right? And then now if we remove this from both sides of the equation, like so, E equals to delta, or why did I say delta? Lambda divided by, remember, this length here will cancel out, which is good. 2 pi r E naught. And with this formula, right? Remember, this is technically a formula right here. But with this formula, you'll notice we still have an r. But in this case, right, the r is necessary because the electric field will vary based on how far you are from this line, right? Remember, we learned that. So in this case, the r is not just the radius of this cylinder, right? So if you think about it, if we made this cylinder really large, it would essentially be the distance. It's not just the radius, but it's also the distance away, for example, if we put a point charge or something like that. So this r here is not a pesky variable. We are going to use this to evaluate electric field. So right here we have a formula. So in this case, right, so all of the above cases deal with charges that are spread out on surfaces and lines. But the problem is, if we are taking into account like 3D objects, right? 3D objects, the calculation of the charge enclosed is much more complicated. And essentially, there are two situations you'll encounter. The first one will be constant volume charge density, and the second one will be charge density as a function of position. So this is going to be a variation on how we can calculate charge enclosed. So in the case of constant volume charge density, the charge is proportional to the volume. Thus, we can simply just use the volumetric charge density, right? Let's let me draw this out, right? So we can simply just use the volumetric charge density. So right here, this is a variation on Gauss's law, right? The variation being that we are going to differ how we calculate Q enclosed. So the charge is proportional to the volume, right? So this will just be equal to Q divided by V, right? So this is generally the best way to deal with this, right? Is if you have a constant amount. With the second case, when the charge density isn't constant, you have to integrate it, right? So we will have to partition Q enclosed into convenient regions of constant charge density and integrate over the enclosed region, which will require integral building once again, right? And as you might expect, the differential volumes you choose will mirror the symmetry of the charge distributions, right? So, and then lastly, before we leave off today, So remember, if you're calculating the potential versus the... Remember, if we're calculating the potential instead of the electric field, remember, we can just integrate, right? So we're going to be using, right, the delta potential equals to negative integral of E times ds, right? Something like so, right? So if we were to calculate potential, for example, this is what we would use. So, nice job today, everyone. This concludes my review of Gauss's law, right? So there's going to be more practice problems in this to help you deal with the variations we just covered, where Q enclosed will vary, how we cover that, right? So be sure to try the practice problems on homework speedmaths.yes.glitch.me. Be sure to check that. It'll be the top link in the description. or should be the only link in the description actually. But essentially that, click there, do practice problems. You need to practice Gauss's law, but I promise you, Gauss's law is going to feel very good once you actually get the hang of it. And typically, for most AP Physics C students, it is one of their favorite theorems and will form our holy grail of AP Physics C, electricity and magnetism, Maxwell's equations.